Okay, dear students, today we will continue the problems on current electricity. Yesterday in the previous session I have completed some 4 problems. In today's session we will continue some more problems of different type. So firstly question number 5 up to question 4 problems have been discussed. Question number 5, 3 resistors 3 ohm, 4 ohm and 12 ohm are connected in parallel. This combination is connected across a battery of EMF 6 volt and internal resistance 0.5 ohm. Calculate the current through each resistor. So this is the problem here. Looks very simple problem and very small problem, but a little bit lengthy it is. We have to find out the effective resistance, then we have to find the current drawn from the cell or battery, and then you have to find out the potential difference or terminal PD of the cell. Then we have to find out the current through each resistor. So to understand it better, let me put the diagram for this problem. Firstly, we can see there 3 resistors are connected in parallel. So we have all learned, so 3 resistors in parallel connection like this it comes 1, 2, 3. 3 resistors are connected like this in parallel. Okay, now this parallel combination of resistors connected across means like this one. So cell of EMF 6 volt and internal resistance small r equal to 0.5 ohm. Okay, so now the current drawn from the cell, let it be I, and 3 resistors are there. Okay, 3 resistors. So I will take here from first one, R1 is 3 ohm. Current I will take say I1, here current I2 through another resistor 4 ohm. Okay, current I3 that is through the resistor R3 equal to 12 ohm. Like this I will write the resistors and resistances. Okay, so R2 equal to 4 ohm. So this is about the diagram for this problem. Now what you have to do, firstly you have to find out the effective resistance. Effective resistance in parallel combination. So I said there are 3 resistors here. So effective resistance of R1, R2, R3 in parallel. So we write. So problem number 5, solution is like this. Effective resistance or equivalent resistance of 3 ohm, 4 ohm and 12 ohm in parallel combination is, so formula is for this parallel combination of resistors, equivalent resistance Rp I will take. We can take Req also we can take. Okay, R effective, Req, anyway you can take, but for my convenience and it is easy to find or write Rp. Okay, so for parallel combination, so 1 by R1 plus 1 by R2 plus 1 by R3, like this we can write effective resistance or equivalent resistance Rp for parallel combination. Now substitution of the values, so 1 by 3 plus 1 by 4 plus 1 by 12. Okay, so this is we can see 12 is the LCM or common denominator. So here 3 it is, here 12 is there. So it is we can say like 4 multiply 4 denominator and numerator, it becomes 4 by 12. So then here, or 12 by 4 is 3, 3 into 1 is 3, like this also you can do. This is our basic maths 1. Now this adding, it is how much? 4 plus 3 plus 1 is 8 by 12. Okay, so this is 1 by Rp. So therefore Rp equal to, effective resistance Rp equal to, I write here also effective resistance Rp. Okay, so Rp equal to reciprocal 12 by 8. 12 by 8 is 1.5 ohm. Okay, 1.5 ohm is the effective resistance of this combination, like this. Rp equal to 1.5 ohm. Then we get terminal PD across the cell. Okay, and to get terminal PD we have to find out the current drawn from the cell. Okay, so current drawn from the cell. To find current drawn, let me simplify this circuit. Now I have single resistor Rp and a cell, that's it. A cell and 3 resistors. Okay, EMF and internal resistance, the current is I through the effective resistance. So total current whatever flows through all the three resistors together, that is equal to the main current drawn from the cell. So main current drawn from the cell is to be found first. So main current drawn from cell, main current drawn from the cell or battery. Here it is given, it is a battery. Okay, so that is written as I equal to main current, let it be I. I have shown in the circuit also. Main current drawn is I. So that I equal to EMF divided by external resistance altogether we got, that is Rp plus internal resistance. Okay. So writing formula is compulsory. For this formula 1 mark will be there. For this substitution simplification 1 mark, like that. So writing formula is very much important in the examination point of view. So EMF epsilon is given for this battery, it is 6 volt. 6 divided by Rp is 1.5 plus internal resistance of the cell or battery is 0.5. Okay, so now 6 divided by 1.5 plus 0.3, so that becomes 2. So the current I is equal to 6 by 2. 6 by 2, that is equal to 3 ampere. So this is the value of current drawn from the cell or battery, main current. Now this current is divided into branches. Now how much it is divided, how it is divided, we cannot directly define. So we have to find out the terminal PD of the cell for that, because the cell is having certain internal resistance. If the internal resistance of the cell is negligible, if it is negligible, then we can find out the current directly actually. Suppose only 6 volt is given in the EMF, no internal resistance not mentioned, then current is very easy. Okay, effective resistance will find, and to find the current directly, that is 6 by 3 is 2 ampere, 6 by 4 is 1.5, 6 by 12 is 0.5. Like that we can get the current directly. But when internal resistance is given, so we have to find the effective resistance of the combination, then current drawn from the battery, then terminal PD of the cell we have to find out, or PD across the parallel combination of resistors. Same it is, terminal PD of the cell or effective PD across the parallel combination is the same. Okay, that terminal PD we have to find out. Okay, so we will find out terminal PD of the cell or battery. Okay, so that is equal to, terminal PD of the battery is equal to V equal to I into Rp. V equal to I into Rp, so that is equal to I. Current drawn from the cell or battery is 3, then Rp value, effective resistance of the parallel combination of resistors, that is 1.5. So this is equal to 4.5 volt. Okay, so this is the terminal PD. Now see, out of 6 volt, 4.5 volt is outside and 1.5 volt potential will be dropped in the cell itself because of the internal resistance. Okay, now what we have to do? Now current through each resistor you can get. So first current through 3 ohm resistor. Okay, so one by one we can write. Current through 3 ohm resistor. 3 ohm resistor is, I have written as I1. Current through 3 ohm resistor is first one, I1. So that I1 equal to, potential difference for the parallel combination is same, V, and same as equivalent circuit. So V by R1. V by R1. So V value, terminal PD or PD across the parallel combination. So that is V value 4.5 divided by R1. Resistance is 3. Okay. So this 4.5 by 3 is 1.5 ampere. So this is the required value. Current through the first resistor is 1.5 ampere. Similarly, current through second resistor, that is 4 ohm resistor. Okay, 4 ohm resistor is I2. Okay, I2 is V divided by R2. V divided by R2. So potential difference across the parallel combination 4.5 divided by resistor. Second resistor is 4. Okay, so 4.5 divided by 4. We can use calculator if needed. So it is 1.125 ampere. So this is the current through second resistor here, 4 ohm resistor. Now lastly, current through the R3, that is 12 ohm resistor, we have to find out. Current through 12 ohm resistor is I3 equal to V divided by R3. Okay, so V 4.5 volt divided by resistor is 12. Okay, so that is equal to 4.5 by 12. You can divide directly. So 4 by 12 is 0.3, 40, 45 means it is 3 again, then 9, 90 means 7. So this much ampere. So this is the current through the 12 ohm resistor. Okay. So out of total current, another way also can get a total current 3 ampere, 1.5 ampere through first resistor. Remaining current should be the last current. That is the remaining of this 1.5 and 1.125. Adding up these two, subtract from 3 ampere. So that is same actually. 0.3375. It comes 0.3375 ampere. So this is the current through the third resistor, that is 12 ohm resistor. So that's all about the problem. So very important problem. They may ask only up to terminal PD in the annual exam. So this year annual exam same question was asked in March 20th. This problem is asked. So the problem idea is very important. Whenever a combination of resistors or combination of cells is given, so you just put the circuit so you get some idea. Suppose you don't get any information or how to solve this problem, so put a circuit diagram, then you get one by one steps. So firstly you have to get the effective resistance of the parallel combination, then we get say like RP here, RP is 3 ohm. Okay, then after getting the effective resistance, find the main current drawn from the cell. This is a simple circuit with one resistance, cell or battery with the EMF and interresistance. So we can get the current here firstly. Then after getting the current, we can find the PD across the cell or battery, that is terminal PD, and that terminal PD will be the same potential drop or difference across the three resistors, because all are in parallel combination. Same potential difference between these 2 points, these 2 points, these 2 points and these 2 points, because all are in parallel combination. So that's all about this problem. I hope you understood this problem. So I will go to the next problem. So I will rub this now and go to the next problem. So the second problem in this is two cells of EMF 3 volt and 2 volt, okay, and internal resistances 1.5 ohm and 1 ohm respectively are connected in parallel across 3 ohm resistor. Calculate the PD across 3 ohm resistor. So that's the problem number 6. So this problem we have to solve. So again I will put a diagram, even though the diagram doesn't carry any mark for solving here, but it helps us. Okay, so here one cell, another cell is there. Okay, and this parallel combination of cells is connected across a resistor of resistance 3 ohm. Okay, so this is the resistor of resistance 3 ohm, and there will be current drawn, and EMF of first cell is 3 volt. Okay, EMF of second cell is 2 volt. Okay, internal resistance of first cell is 1.5 ohm, and internal resistance of the second cell R2 is 1 ohm. And we have to get the potential difference across the resistor 3 ohm, that is this external resistor PD we have to get. Again we observe the parallel combination of two cells are there here. Okay, effective or equivalent EMF of the parallel combination and equivalent internal resistance we can find out. Then it becomes a single cell, equivalent cell of certain EMF and certain internal resistance. Then we can find the current through this resistor. So this circuit is equivalent to, I can write, single cell, okay, and resistor as usual, given 3 ohm resistor. So let it be R, and here also this equal to R, and I is the current through that resistor. Separately the currents may be I1 and I2. Here it is not required to find out the currents individually, directly. So and EMF I will take epsilon equivalent, epsilon EQ, parallel combination of two cells, and equivalent internal resistance say Req. Okay, so like this we will take. Now you have to find out the equivalent internal resistance and equivalent EMF. So two resistors are in parallel, like two cells are in parallel means equivalent internal resistance also found directly. Equivalent resistance we found by derivation expression is that equivalent internal resistance. So problem number 6, equivalent internal resistance. Internal resistance is given by, it is for two resistors. Actually for n resistors 1 by Req, 1 by n cells, 1 by Req is 1 by R1 plus 1 by R2 plus 1 by R3 etc. If there are only two cells, then we can directly write Req is R1 R2 R divided by R1 plus R2. Okay, this is very simple, like two resistors in parallel also same. If the two resistors with the resistance values R1 and R2 connected in parallel, effective resistance for two resistors is R1 into R2 divided by R1 plus R2. We will take capital R1 and capital R2 for external resistances. This is for internal resistance of the cells. So small letters are used. Okay, now substitution. Internal resistance is 1.5, first one. Second one is 1 divided by 1.5 plus 1. Now multiplying 1.5 into 1 is 1.5 divided by 1.5 plus 1 is 2.5. Now we can divide this 1.5 by 2.5. It is like 15 by 25. 150 by 25 is 6. So 1.5 by 2.5 is same as 15 by 25. 150 by 25 is 6. So 15 by 25 will be 0.6. Or otherwise you can use a calculator also. Okay, so this is the Req value. Now we can write the expression for equivalent EMF. We have to find out the equivalent EMF of the cell. Equivalent EMF of the cell. Equivalent EMF of two cells is epsilon EQ given by, so given by the expression epsilon EQ divided by Req, okay, equal to epsilon 1 by R1 plus epsilon 2 by R2. Okay, so then next, okay, so now substitution here. Substitute 1 by 1. Epsilon EQ is the required value. Req, we got it already, 0.6 ohm. Okay, 0.6 ohm. That is equal to epsilon 1 by R1 is 3 volt divided by 1.5 plus EMF of the second cell 2 volt divided by its internal resistance 1. Now we have to simplify this. So that is 3 divided by 1.5 is 2. Plus this one also 2. So that is equal to 4. 2 plus 2. 3 by 1.5 is 2. Okay. So now epsilon EQ will get. Therefore, epsilon EQ equal to 0.6 take into that side. 0.6 into sum it is 4. So that is equal to 2.4 volt. 2.4 volt is the equivalent EMF. Okay. Now we got the equivalent EMF, we get the current I now. So using the expression current drawn from a cell, we can get the current value drawn from the equivalent cell, not each cell. Cells may have current, maybe currents I1 and I2, but total current one will get here because we consider the equivalent cell of the combination. So current drawn from equivalent cell or current given by equivalent cell, and the same current flows through the external resistor 3 ohm. So current through 3 ohm resistor, that is same I said, current through 3 ohm resistor is same as the current drawn from the equivalent cell. So that is equal to I expression is I equal to epsilon EQ. Now instead of two cells we have to consider single cell whose EMF is epsilon EQ. Then external resistance say R is there plus its internal resistance is taken Req. Now substitution epsilon EQ we got 2.4, okay, divided by external resistance 3 ohm, okay, plus effective internal resistance is 0.6. 0.6. So now division I equal to 2.4 divided by 3.6. Okay, 3.6, that is equal to 2 by 3. 24 by 36 is 2 by 3 ampere. Okay, so this is the current. If you want decimal value, we can round off to two significant figures. Actually, it comes 0.6666 like that. Okay, 0.667 ampere I can write. Now, the terminal PD or PD across the resistor is the question. PD across the resistor, that is 3 ohm resistor, is required in the question. So, PD across 3 ohm resistor. PD across 3 ohm resistor is using simple Ohm's law given by V equal to I into R. Okay, so I current through that is 2 by 3 only. I will take exact value, I get 2 by 3, and resistance is 3. So the answer is this 3 and this 3 cancels. So the terminal PD or PD across the 3 ohm resistor is 2 volt. So this is the answer required. So the idea is finding first equivalent resistance of the two cells, okay, and equivalent EMF of the two cells. Then replace the combination of two cells by single cell of certain EMF and certain interactions. Then find the current. Then find the PD across the 3 ohm resistor just by using Ohm's law. And alternatively, this problem can be solved with the help of Kirchhoff's loop rule. Kirchhoff's loop rule also we can take, apply, and we can solve. In another session, I will discuss problems on Kirchhoff's loop rule, and similar question I will take and solve. Okay, so that's the end of the question number 6. So I hope you understood this problem. So this is also appear in one of the annual exams. So I go to the next problem, that is problem number 7. A cell supplies a current of 0.9 ampere through a resistor of 2 ohm and a current of 0.3 ampere through a resistor 7 ohm. Find the EMF and interaction of the cell. This is a very simple question. So here there is a cell and variable resistor. First case resistor is 2 ohm, current drawn from the cell is 0.9 ampere. Second case there is another resistor of 7 ohm and the current drawn from that cell in that through that resistor is 0.3. That means the cell is fixed here, but the resistor in two different situations, different values. So this is the resistor R and this is the current I. This is the EMF say we don't know, question mark, and R also we have to find out. So two situations, two equations we get. We have I value for particular R value and another I value for another R value. That means this resistance varied in the circuit. So the current in the resistor also varies. Same cell, okay, cell is same means its EMF and interactions will be same in both the situations. Now the formula already we studied, EMF equal to I into R plus R. Okay, this is the formula, and we derived current drawn from the cell I is EMF, current given by the cell or current passing through the external resistor, it will be same. So this is the formula what we derived in the theory part, and this derivation usually they ask for 3 marks. Now using this formula, first case, okay, we don't know EMF here and we don't know internal resistance. We know I value, we know R value. Two cases arises here as in the problem given. So first case, EMF epsilon equal to current I. Current I is equal to how much? First case current is 0.9. Okay, 0.9. R plus R is also given in this problem. Correct? So first case R is 2 ohm. Okay. So 2 ohm plus internal resistance don't know. So let it be equation 1. Then second case, EMF epsilon unknown. Second case resistor is 7 ohm, current is 0.3. So the current is 0.3, I substitute in place of I. Then external resistance connected in this situation 7. Okay. If 7 ohm resistor is connected to the cell, same cell, current through that 7 ohm is 0.3 or current drawn from the cell is 0.3 ampere. Okay. So these two are the equations. We have to solve these two simultaneously equations in EMF epsilon and internal resistance R. So easiest way is we have to find out both the EMF and internal resistances. So equate epsilon same. Hence from equations 1 and 2 we can write from 1 and 2. What we can write is say this side I write 0.9 into 2 plus R equal to 0.3 into 7 plus R. Okay. Now we can divide this 0.3, we can bring this side. When you bring this side 0.3, 0.9 divided by 0.3, okay, into 2 plus r equal to 7 plus r. Now 0.9 by 0.3 is same as 9 by 3. 9 by 3 is 3 meters. So 3 into 2 plus r equal to 7 plus r. Now expanding 6 plus 3r equal to 7 plus r. So now what we get is, bring r this side, so it is 2r. 3r minus r, if you simplify it is 2r. Then 7 is there, take 6 that side, 7 minus 6 is 1. This implies resistance R equal to, internal resistance of the cell is 1 by 2 ohm or equal to 0.5 ohm. So this is the internal resistance of the cell. They asked to find out EMF of the cell also. So to get the EMF, substitute the internal resistance value in any one of the equations. So first equation or second equation. Okay, go for first equation. Using the R value 0.5 ohm in equation 1. Okay, in equation 1, substitute. So EMF epsilon equal to 0.9 times 2 plus internal resistance we got 0.5. That satisfies both the equations actually. R value 0.5 ohm satisfies first equation also, second equation also, hence EMF also. So EMF epsilon equal to 0.9 into, so 2 plus 0.5 is 2.5. So 25 into 9 is 225. So this product is 2.25 volt. So this is the EMF of the cell. So the problem here is a cell is there whose EMF and internal resistance is not known, but a resistor is connected. First 2 ohm resistor is connected, 0.9 ampere is the current through that resistor, and 7 ohm resistor is used here and current through that is 0.3 ampere, and we are asked to find out EMF of the cell and internal resistance of the cell. Then next is another problem. Okay, so problem number 8. Let me go to the next problem. I hope you completed this problem and understood the method of solving. The next problem is okay, problem number 8. Okay, so there is a problem related to temperature coefficient of resistivity. Let me read the question. Resistance of copper coil is 4.64 ohm at 40 degrees Celsius and 5.6 ohm at 100 degrees Celsius. Calculate the temperature coefficient of the resistivity and resistance at 0 degrees Celsius. There is a copper coil. We know that copper resistance of the copper or resistivity of the copper depends on its temperature. As the temperature increases, resistivity and resistance both will increase. So here are the two situations given. At 40 degrees Celsius, the resistance is 4.64 ohm, and at 100 degrees Celsius, that copper coil has a resistance of 5.6 ohm. That means the resistance increases. Okay, and we have to find out the value of alpha. Temperature coefficient of resistivity is nothing but alpha. Then resistance at reference temperature says 0 degrees Celsius. So these two values you have to get here also. It is also a 5 marks question. Now firstly, let me write the problem in symbols. Okay, so first formula. Which formula is suitable or relevant to this? Resistance at any temperature T equal to resistance at reference temperature or 0 degrees Celsius times 1 plus alpha into T minus T naught. Like this you can write. I can write in capital letters also. Okay, T minus T naught, reference temperature. Okay, here I write capital letters, no problem. So resistance at any temperature T is resistance at reference temperature. That is temperature is T naught, and this RT is the resistance at T, and alpha is the constant, that is temperature coefficient of resistivity. So now first case, like previous problem, only two cases are there here. First case, resistance is 4.64 ohm. Okay, equal to R naught value we don't know. Then 1 plus alpha value also don't know. Then T minus T naught. 40 degrees Celsius is the resistance at 40 degrees Celsius. Resistance is 4 points. So 40 minus, first case is T1, resistance is R1. So 40 minus reference temperature is 0. Okay, so like this. Now that is 4.64 equal to, from got 4.64 equal to R naught into 1 plus 40 alpha. Now second situation, resistance is 5.6 ohm. For the coil resistance is 5.6 ohm. Second case, resistance 5.6, R naught don't know, we have to find out. 1 plus alpha into the temperature is 100. So 100 minus 0. Okay, simplification 5.6 equal to R naught times 1 plus 100 alpha. 100 minus 0, 100, 100 into alpha, 100 alpha. Okay, so this is the second case. Now to solve these two equations, R naught and alpha, two unknowns, two equations. We can divide the one equation by another equation. Then also we will get the value of alpha. We get the value of alpha because R naught cancels. Or we can multiply 2.5 to the first equation. So 2.5 into 40 is 100 alpha, and here 100 alpha is when you subtract one equation from another equation, you can cancel alpha. Alpha cancels, only R naught remains. So we can get the R naught value first. Then to get the alpha value, substitute in either equation 1 or equation 2 to get the value of R naught. So now what we can do is, okay, so I divide the equation 2 by 1. Equation 2 divided by equation 1. Equation 2 divided by equation 1 gives, okay, so it gives 5.6 divided by 4.64. Respectively you have to divide, that means LHS divide equation 2 5.6 by 4.64 equation 1. Now here equal to R naught times 1 plus 100 alpha divided by R naught times 1 plus 40 alpha. So this is what we get. Now cancel, R naught and R naught cancels, cross multiply. So 5.6 or else, yeah, we can do cross multiplication, that is the better. Then we can simplify the alpha value. Okay, so that is okay, so cross multiplication or take the ratio, that's also okay. So 5.6 divided by 4.64 is 1.207 is 1.207. This is the ratio of LHS. Then here 1 plus 40 alpha is there in the RHS. I bring to the LHS 1 plus 40 alpha equal to 1 plus 100 alpha. Okay, so this is what we have. Now multiply this 1.207 plus 40 into 1.207. Okay, so 40 into 1.207 is 48.28. 48.28. Okay, so 40 into 1.207 is 48.28 alpha equal to 1 plus 100 alpha. Now we have to get the value of alpha. So bring this 1 here. So 1.207 minus 1 is 0.207. That is equal to, okay, so take 48.28 that side. So 100 minus 48.28. So it is 51.72 alpha. So the value of alpha is okay. So that is this number is there extra. You have to divide. So 0.207 divided by 51.72. So this is the value of alpha. So basic mathematics. So here 1 plus 40 alpha is there in the denominator. You can do cross multiplication, subtraction and simplification. And otherwise first we find the ratio of this. It is not exact number, approximately I have rounded off. So then simplify. Okay, anyway it's okay. So now 0.207 divided by 51.72. So that is 0.004. 0.004. So this is the value. Okay, unit of alpha. See the temperature is here, alpha into temperature. So this is 1 here, this is alpha into temperature. So 1 is unitless or dimensionless. So alpha into temperature should be dimensionless. So therefore alpha should have the unit of reciprocal of temperature. So therefore we can write per degree Celsius or per Kelvin. Both are okay, per degree Celsius or per Kelvin. So this is the value of alpha. After getting the alpha value, put any one of the equations. I will substitute in second equation as there is 100. So using alpha equal to 0.004 in equation 2. In equation 2, what I have is here 5.6 in the LHS equal to R0 into 1 plus 100 alpha. So 1 plus 100 into alpha is 0.004, what we got by previous calculation. Now 100 into 0.004, it is the matter of shifting the decimal point 2 digits right, multiplying by 100 or use calculator only. So 0.4 it is. So 100 into this becomes just 0.4, 0.4 added with 1. Okay, so 5.6 equal to R0 into 1 plus 0.4. Okay, so it is 1.4 R0. Okay, so I will do here. So 1.4 R0 equal to 5.6. Therefore R0 equal to 5.6 upon 1.4, that is equal to 4. 56 by 14, so 4 ohm. So therefore resistance of the copper coil at 0 degree Celsius is R0, that is 4 ohm, and temperature coefficient of resistivity is alpha, that is 0.004 per degree Celsius. So this problem can be solved in both the ways. Actually equation 1 multiplied by 2.5, so then it becomes 100 alpha, and here 100 alpha we can see. Then subtract after say equation 3 we take 4.64 into 2.5 R0 and 2.5 here, and this is 100 alpha. Subtract equation 3 and 2, we get the difference, and in terms of R0 we get, so we get first value of R0, then we have to find out the alpha value. Here by dividing one equation by another equation, easily we can see R0 cancelled. We got the value of alpha, then we found R0 value using the alpha value. Okay, so like this, this is the problem based on the temperature dependence of resistance of a copper coil at two different temperatures and finding R0 value. Now we will move to the question number 9. Very simple question for 2 marks. A 220 volt 1 kilowatt coil is connected across 110 volt main supply. What will be the power consumed by it? So there is a coil, standard operating voltage actually 220 volt, or normal household circuit, RMS value of voltage is 220 volt, and its power rating is 1 kilowatt. Now if such a coil is connected to just 110 volt power supply, not 220. Actually operating voltage is 220, but we have voltage in the house, say, suppose it is not in India it is 220 volt only. But in the problem, if it is given, you have to take the same. Suppose that 220 volt 1 kilowatt coil is connected to 110 volt main supply. What power it consumes? Its actual power rating is 1 kilowatt at 220 volt. Now the voltage is reduced, so operating voltage reduces means automatically its power consumed also reduces. So that is the problem. So here what we have to do here, the problem given data is power value and operating voltage. Okay, but the actual voltage of the applied voltage is lesser. So we get the resistance. First we can get the resistance of the coil. So we have the relationship between power, voltage and the resistance. So we have, okay, power P equal to the problem number 9. Okay, problem number 9, last problem in at the bottom. So problem number 9, power equal to power of the coil, actual power P equal to is 220. I write P1 because second case we have to get the power and the later voltage at 110 voltage. So P1 is the power, that is 1 kilowatt. I write 1000 watt, and operating voltage is 220 volt. Now to get the resistance is how much? Resistance will be same in both the cases. As the voltage changes, resistance of the coil will not change. Only voltage changes, power consumed will be different. So relation connecting power, voltage and resistance. So that is power P equal to V square by R. This is the relation. So using this first case, what happens? Power P1 equal to V1 square divided by R. So therefore resistance R equal to V1 square divided by P1. Okay, so V1 square. So V1 square is 220 into 220. Actually 220 square we have to do. 220 into 220 divided by 1000 watt. 1000 watt, 1 kilowatt is 1000 watt. Now cancellation 0 0, here 0 0 cancels, 100 is there in the numerator extra. So now this is 22 into 22, 484 divided by 10. 484 divided by 10. So 48.4 we can write, or let it be like this only, 48.4 ohm. So this resistance will be the same in both the situations. Whenever you connect different voltages, resistance of the coil is property of the coil. Here we have not changed the temperature, so it will have the same resistance. Now in the second case, voltage is 110 volt. So power dissipated in the later case. Power dissipated when 110 volt applied. 110 volt is applied by this coil. How much power is dissipated? So P2 is, same formula, P2 is V2 square divided by R. So voltage applied in the second case 110 volt. So 110 into 110, 110 into 110 divided by resistance is 48.4. Okay, 48.4. So this simplification, 11 11 is 121, then 2 zeros, or you can use simple calculator, 48.4. Okay, you have to divide this. So 12100 divided by 48.4. So it comes exactly 250. So 250 watt is the power consumed by the coil or heater, say at 110 volt. So in a shortcut we can do this problem actually. So as the power is shortcut method, even in competitive exams you can use this method only. Power is say resistance same, P equal to V square by R. So which implies power is directly proportional to square of the voltage. So P2 by P1 is equal to, see why this we can write like this, because resistance is the same in both the situation. So with that idea we can write P proportional to V square. So P2 by P1 equal to V2 by V1 whole square. Now substitute. So P2 equal to P1 into so V2 by V1. Second case voltage applied 110. So 110 divided by 220 in the first case, actual operating voltage. So square of this. Now P1 value, actual power dissipated 1000 watt in the standard operating conditions, that is 220 volt is applied. Okay, so 1000 watt. 1 kilowatt is 1000 watt. So this is 0 0 cancel, 11 by 22 is half square. Okay, now 1000 into half square. Okay, 1 by 2 square is 1 by 4. 1000 by 4 is 250 watt. So easily we got this answer in a shortcut way. This is also accepted. Okay, so because finding resistance is not compulsory as the question says here. Only they ask what will be the power consumed. Maybe 2 marks question you can do this way only. And even CET and other competitive exams also shortcut we can use. Okay, so the idea is resistance will be the same whenever you connect any device to any voltage. Resistance will remain same, but the power consumed will be different depending upon the voltage value. If you connect to lower voltage, lower power is consumed by the device. Okay, so that's the idea, very simple, using the expression for power V square by R. And first we will get the resistance of the coil, then use that resistance in the second situation, and the voltage we have here 110 volt, so power consumed is 250 watt. So that's the idea. And lastly one problem here, question number 10 I discussed. So I hope you completed this and understood this problems. Next is problem number 10. So look at the circuit carefully. There is a circuit, and in this circuit we have to calculate current through each resistor. So there is a battery of 12 volt EMF and 1.2 ohm internal resistance, and 2 branches are there here. In one branch there are 2 resistors in series, 4 ohm and 8 ohm. In another branch there are 2 resistors, 2 ohm and 6 ohm in series. Now this is series, so the same current flows here I1 and the same main current is I, and here in the current through second branch say I2. Okay, so I2. So what we have to do now here, first we have to get the effective resistance of the combination. So firstly, okay, so this 4 ohm and 8 ohm in series, 2 ohm and 6 ohm in series, will simplify. Then parallel combination of two resistors, then effective resistance. Then we can find out the main current. After finding the main current, we have to find out the terminal PD of the cell or battery. Then we can get the current to each resistor. So that's the method for this problem. Even if it is internal resistance is 0, then the problem will be very easy. Just total resistance is here say 12 series. 4 and 8 series means 12 ohm. So 12 volt by 12 ohm is 1 ampere through here, and 12 by 8, so 1.5 ampere. But as it is not 0, internal resistance is not 0, 1.2 ohm is there. So the terminal PD is not 12 volt, only EMF is 12 volt. Terminal PD we need, otherwise we can't find the current to each branch. So firstly, let us solve one by one in steps. First we will get effective resistance of 4 ohm and 8 ohm in series. Effective resistance of 4 ohm and 8 ohm in series. The formula for series combination of resistors RS is R1 plus R2. Okay, two resistors in series. So RS is R1 plus R2, 4 plus 8, that is 12 ohm. Similarly, effective resistance of or equivalent resistance of another branch, 2 ohm and 6 ohm in series. These two resistors give again RS dash, right, say R3 and R4. So the resistors 2 and 6, so that is 8 ohm of the second branch. So first branch is 12 ohm and second branch is 8 ohm. Now the parallel combination. So we have the resistors. So let me redraw the circuit here, or I have this part here only. Yes. So this is 8 ohm resistor and this is 12 ohm. So the circuit will be like this now. Two resistors parallelly connected now. Instead of 4, only 2 are there, because we simplified the equivalent in each branch. So this is a 12 ohm resistor and this is the 8 ohm resistor. And current will be the same. In first case we had I1 and I2. Now equivalent also same current flows. Okay, so 12 volt and 1.2 ohm. Okay. Now currents you have to get I1 and I2. Okay. So then to get the current, firstly effective resistance of this parallel combination we have to get here. This effective resistance. So that is equal to, now one more circuit let me draw. It becomes complete. Single resistor of say Rp here, and terminal PD V here, and terminal PD here also V only, and here also V only. Terminal PD will remain same if you find the equivalent resistor or effective resistance of combinations. Okay, now what you have to do is effective resistance of the parallel combination. Okay, so effective resistance or equivalent resistance of 12 ohm and 8 ohm. 12 ohm and 8 ohm in parallel combination. In parallel they are. Okay, so that is Rp formula for two resistors in parallel, R1 into R2 divided by R1 plus R2. But we have here Rs and Rs dash. So we'll substitute Rs into Rs dash, or we can also write R1 R2 divided by R1 plus R2. But we have taken R1 R2 for this resistors. So Rs plus Rs dash. Okay. So now this Rp value is, substituting the values. So 8, first one 12, then one 8. So 12 into 8 divided by 12 plus 8. Okay. So 12 into 8, 96 divided by 20. That is 48 by 10 or 4.8 ohm. This is the Rp value now effectively. So that is 4.8 ohm effective resistance of all four together. Okay, external circuit. Then internal resistance and EMF are given. Internal resistance small r is 1.2 volt, 1.2 ohm. So now we can get the current, main current drawn from the battery. So main current or the current drawn from the battery we get here I equal to epsilon divided by external resistance, here Rp. Simplified all the resistors we get only Rp plus small r, okay, internal resistance. So EMF 12 volt, okay, divided by Rp, external resistance effective value we got here 4.8 plus internal resistance is 1.2. So 12 divided by 4.8 plus 1.2 is 6. So that is equal to 2 ampere. The current drawn from the battery is 2 ampere. Now that current 2 ampere divided into two branches. For finding that we need a terminal PD of the battery also. So terminal PD formula already we discussed in the earlier problem. Okay, so terminal PD across the battery is V equal to I into effective resistance Rp it is, so I into Rp. So V equal to I into Rp. So I is 2 ampere, resistance Rp effective value 4.8. So the terminal PD is 9.6 volt. So terminal PD across the battery is 9.6 volt. Now we can get current through each branch. First branch I1. Okay. So current through first branch is that is the same current through 4 ohm and 8 ohm. So that is I1, and 2 ohm and 6 ohm current is I2. So current through first branch or current I1 is PD across both the branches will be the same as it is parallel combination. So V divided by this branch I took the resistance as Rs, and the second branch is say Rs dash. Okay, so V divided by Rs. Okay, first branch effective resistance Rs is to be taken, not 4 ohm or 8 ohm together effective value. So it is V divided by 9.6 divided by terminal PD divided by or PD across the branch is same as terminal PD. Okay, so that is 9.6 divided by Rs value, that is 12. Rs is 12 ohm here we got. So 9.6 by 12 is 96 by 12 is 8. So 9.6 by 12 is 0.8 ampere. Okay. So another current through the another branch is I2. Current I2 in the second branch is V terminal PDV divided by second branch total resistance, that is Rs dash. So Rs dash. So that is 9.6 upon second branch effective resistance 8. So 9.6 upon 8 is 1.2 ampere. So this is about the branch currents. So main current we got 2 ampere, that divides into two branches, 0.8 ampere and 1.2 ampere. That's all about this little bit lengthy question. So branch currents you have to get means as there is internal resistance in the cell, it is not zero. If it is zero, very simple, just we use Ohm's law, V equal to IR. So I1 is V divided by R effective. But here we have to find out first effective resistance of the entire circuit. Then we have to find out the main current drawn from the cell. Then we have to find out terminal PD of the cell or the battery. Then we will get first branch current, second branch current using Ohm's law. That is a simple Ohm's law only. V equal to I1 into Rs. Okay, so first branch PD. So therefore current I1 is V by Rs. Same way the branch current 2, that is I2, is potential difference across the branch is same as terminal PD of the battery. So V divided by Rs dash. So 9.6 by 8, that is equal to 1.2 ampere. So like this we will get. So still more of problems are there to discuss. In another session I will discuss circuit analysis and Kirchhoff's loop rule and junction rule. Okay, so that's the end of today's session.